Lindenstrauss will tell us about rigidity of higher-rank diagonal actions and applications.
Thank you.
Just making sure the microphone is on.
That's a good idea, but it's on. So yesterday's talk, we talked about essentially about unipotent dynamics, about actions of group like this group acting on quotients of some quotient spaces. Today we're going to look at a different kind of action, something like the diagonal actions, but let's even start. Today maybe we would look at the action of this group acting on some space like that. But I promise that this would be not a second talk, but a first talk, that it's sort of going to be independent from what happened earlier. So let's start at the beginning, at the very beginning. So one thing before I forget, most of what I'm going to talk about is joint work with Manfred Einsiedler from ETH. Of course, I'll mention lots of work with other people, but whenever I mention work of myself, more likely than not, it will be joint with Manfred. And let's sort of start with some basics. So maybe I have some space X, and it will be convenient for me to assume that space X is maybe a locally compact second countable space, topological space. And then I have a Borel measure mu is a probability measure. X. And then I have a map T from X to itself that preserves the measure mu. And then if you have such a triplet, I would say that the definition mu is ergodic. Well, you could define it in several ways, but one way is to say if it is an extreme point in the convex compact set of T invariant probability measures, and another way to say that it has there exists no non-trivial T invariant sets. Every T invariant set either has measure 0 or its complement has measure 0. So these are two equivalent definitions. And under these conditions, then of course you have the point-ergodic theorem, or if you like, a small variant of this. So if I have an ergodic system, then for almost every for mu almost every x, mu almost every x is mu generic, which means that for almost every x in sorry, what is mu generic? That I already had for almost every in this sentence. I don't need it twice. So for any continuous function, maybe I didn't assume my space is compact, so maybe out of safety I'll take it to be compactly supported. If I look at the ergodic averages, this would converge to the average of f with respect to the measure. And if mu is some kind of canonical measure of the space, then I would just say if mu is sort of the natural space, the natural measure on my space X, I can say that that the sequence becomes equidistributed. So here's an example. Really want to start with simple things. So I'm looking at a quotient space, but not a very frightening quotient space. I divide the real numbers by the integers. I have a circle, and if a is an integer, I can look at the map TA, which takes x to ax mod 1. It's a nice map. It's certainly ergodic, very easy to see. So for almost every x, ergodic with respect to, I should mention this, right, I have a triplet I need to talk about, a space, a map, and a measure. So of course, for m, which is the big measure, which is a natural measure here. So for almost every x, this Ta to the nx is equidistributed, which is equivalent to having that the number x is normal to base A. And now, so this is true for almost every point, but there is a full house of dimension of points for which the sequence is not even dense, so obviously it's not going to be equidistributed. And there are sort of, you get some kind of mathematical Murphy's law. So for almost every point, for almost every, you have that x is normal to base A, or the sequence is equidistributed, whatever you want to. But you don't have any, but not known for any natural x. Of course, you could construct a number that's going to be normal to base x. You could easily write a program that would write a number. But if you look at some algebraic number or pi or something, nobody knows if it's normal to base A. And here's sort of another example, which would be more related to things that we'll talk about later. It's somehow not a continuous example, but it's okay. The discontinuity is mild, so let's ignore it. So again, we have a map T from 0, 1 to 0, 1, maybe half open interval this time, not so important, which takes a number to 1 over x minus the integer value of 1 over x. And just to be very pedantic, let's say that T of 0 is 0. So now you know how I map every point. And it preserves a measure. It doesn't preserve Lebesgue measure, but it preserves a measure which is in the same measure class. This measure, Gauss measure, which for set A has density 1 plus x. Okay, so this is a measure which is preserved by this action. It's actually ergodic. So for almost every, and this map is of course very closely connected to the continued fraction expansion of a point, right? So continued fraction expansion of x, right? So you write it as, right, you write x being a0 plus 1 over a1 plus etc. But it's nicer to put it in some kind of compact notation. So okay, I'm taking x between 0 and 1, so the first digit is 0. and then I'm going to take some function of x, we'll talk about it as the first digit, and then the same function of t of x as the second digit, etc. Well, this function, of course, is the integer value of 1 over x. Right? So if you look at this function, integer value of 1 over x, along an orbit, you exactly read off the continued fraction expansion of a number. And because of the fact that the measure is ergodic, then for almost every x, whether Lebesgue or according to the invariant measure, because they're absolute continuous ones with respect to the other, you could see that, for instance, the frequency of a digit a in continued fraction expansion of x is the measure of the appropriate interval, which turns out to be log 2 of something like a plus 1 squared over a plus 2a. And yeah, so this number is bigger than 1, so at least this is a positive number, which is a good thing for a frequency. But somehow the only natural x for which we know something about the continued fraction expansion, they are atypical. So for instance, if x is quadratic, something like, right, it's sort of in a field of degree 2 over q, irrational, then continued fraction expansion of x is eventually periodic. Certainly not a typical behavior, and E has a very nice continuous fraction expansion. Very nice continuous fraction expansion, but it's certainly not typical, or E squared has a nice continuous fraction expansion. There's a formula here, but maybe I won't. I'll leave you guessing what the rest of the formula is. I know nothing about E cubed, might well be a typical number, but then we don't know how to prove anything about it. Or another number that I would have been extremely happy to prove anything about its continuous fraction expansion is cubic root of 2. Or you look at the cubic root of 2, is a continuous fraction expansion of this typical, or even is a continuous fraction expansion of cubic root of 2 unbounded? Do you have arbitrarily large digits in this continuous fraction expansion? It's not known, and okay, because it's not known, then obviously it's hard to approach from any direction that we know how to approach this. But in particular, my set of tools using dynamical systems, if I would like to attack such a thing, I need to somehow identify a special property of this number cubic root of 2 that somehow plays nicely with the dynamics, that I could use it to show that cubic root of 2 is not one of this full house of dimensions set of points which behave atypically. Okay, so this is sort of the difficulty here. Now, in 1967, Furstenberg discovered an interesting phenomena. So this is sort of the higher rank rigidity, and the simplest case of that is something that Furstenberg discovered. So here's Furstenberg in 1967 about. You don't look just at the, you look at the semigroup where you multiply not just by powers of A, but by powers of A or powers of NB. So nk are bigger than 0. Integers. Okay, and A and B are multiplicatively independent integers, which basically means that log A over log B is irrational. So this action of the semigroup, even though each individual element is exactly one of these things that we said, most orbits behave one way, but many orbits behave another way. This is much more rigid than what's generated by a single map. So in particular, Furstenberg proved something and he conjectured something. Does
this refer again to the operators on the circle?
Exactly. So this is, I'm looking at, so I'll make this clear now. After I state the theorem, it will be, would sort of save me a bit of chalk. Any SAB orbit on R mod Z is either eventually periodic maybe I don't want to define what eventually periodic would mean in this context, but just say finite, or dense. Right, so what I'm looking at, right, I'm looking at the number x, and I'm looking at a to the n, b to the kx, mod 1, where n and k are positive integers, and I'm looking, so either this is finite, if x is rational, this is finite, and if x is irrational, then this is going to be dense. That's what Furstenberg proved. It's not a hard thing to prove nowadays, but it's sort of a remarkable insight that this is not just a curiosity, but a important phenomenon. And then there's something which is presumably somewhat harder to prove because it has been an open problem since '67, conjecture, which Furstenberg never put to print but has been hugely influential. That any measure on the one-thos invariant under the semigroup is either finitely supported measure on a periodic orbit, finitely supported, what I called a periodic orbit for this group in my previous lecture, or is Lebesgue measure. And the famous, so that because this is conjecture is open, the famous result toward that is the theorem of Rudolph and Johnson. So Rudolph proved it for A and B relatively prime, and then Amy Johnson extended it to the general case. Any SAB invariant and ergodic measure mu on the one-tos is either a Lebesgue measure, or that is singular, let's say, singular. So I don't even need to say ergodic if I say it this way, that's an advantage. So every invariant measure mu on R modulus is singular with respect to Lebesgue measure satisfies that the entropy of the measure with respect to, let's say, the times A map is 0. And okay, I'm going to talk about entropy, but I haven't done it yet. So an equivalent formulation, if you don't know what entropy is, for mu almost every x, if I look at the measure of a ball of radius r around x, so that's just a fancy way of saying, right, the interval between x minus r and x plus r. You take the log of this, you divide by log of r, goes to 0. So if you believe the conjecture, then a measure which is invariant and singular with respect to the Lebesgue measure has to be purely atomic. There will be points for which the measure is, all of the measure is concentrated on a countable set of points. Here, this is a weak form. You don't actually see that there's a mass of the individual point, but the mass of small neighborhood of a point decays very slowly. That's what this statement says. In particular, this implies that the Hausdorff dimension of the measure mu is 0. Now, there's also somehow an analogous situation for if you have commuting automorphisms. So d by d integer matrices commuting with one another, and they are multiplicatively independent. I guess not powers of the same matrix, and I'm going to assume that they act totally irreducibly on the torus, that there's no finite collection of subtori which is invariant under both multiplication by A and multiplication by B. And then again, an invariant measure is either a Haar measure or has 0 dimension in this sense, or entropy. Well, it's true for integers, and I'm saying this is the definition I'm going to take here. That's also how I'm going to define multiplicatively independent here. Now, okay, so this was sort of a prologue. Now let's talk about really what I wanted to talk about, the situation for in homogeneous dynamics and quotients of groups. So now let's look at some group. I'm going to look at the group G, some linear algebraic group. And maybe gamma in G is going to be an irreducible lattice. So maybe I won't even take a general linear algebraic group, but I'll take semi-simple linear algebraic group. Don't worry too much. So take maybe SLN or products of SL2s. That would be good. And actually, I'll be more specific. I'm going to take G to be a linear algebraic group over the rational numbers. So I'm going to take some subgroup of the group of D by D matrices defined by some equations with integer coefficients. And then I can plug in, I can look at the real solutions of this set of equations, and I can look at the integer solutions of the set of equations. This is obviously going to be well, if I define this thing a bit carefully, this is going to be a subgroup of GR, and if my group G is semi-simple, it's going to be a lattice, so gamma is a discrete subgroup of G, and it's actually a lattice in the cases that we would look at, for instance, if the group is semi-simple. And now, what would be the analog of this times 2 times 3 system? So basically, I'm going to try to look at the action of subgroups, which are the opposite of the kind of groups we considered in the previous talk. So I'm going to look at some A inside G, which is diagonalizable. Let's say, so it's an abelian group, and you can simultaneously diagonalize it, let's say, over the complex numbers. And I'm going to try to make an assumption that would correspond to this multiplicatively independent or something. So the definition, A is of closed, A is of higher rank if there is a proper group homomorphism phi from Z2 to A. This is not an algebraic group homomorphism, but just an abstract group homomorphism, or a homomorphism of topological groups, because I'm talking about proper. So basically, there are two independent elements in my group A. That's what it means. And then you could sort of would like to prove or conjecture or something the following statement, to prove or conjecture the following naive conjecture. So I'm just saying that any compact subset of A contains only finitely many elements. So you don't have, this doesn't bunch, you have an honest Z2 inside that doesn't somehow accumulate to anything. A is an abstract. A is a subgroup which of a algebraic group, but it's just a subgroup. some subgroup, maybe the group generated by two elements, which can be simultaneously diagonalized. So you could find everything lives inside some SLD, some field, and you could look at over the complex numbers, and you could simultaneously diagonalize them. So it's not unipotent. That's sort of a key thing. Let's see. Maybe I'll go to the other side out of some kind of fairness. So what would be the naive conjecture? So if A is of higher rank, any A invariant and ergodic measure on such a quotient G mod gamma is homogeneous. Okay, what do I mean by this word homogeneous? So a measure mu is homogeneous if you look at the stabilizer of mu in my group G. It acts transitively on the support of mu. Okay, so all of the elements of my group that preserves, I have a G mod gamma, I have some, I'm looking at homogeneous dynamics. It's homogeneous because there's some action of some group which maps every point in my space to every point. This is a group G. And I'm looking at the subgroup of this which fixes my measure mu. It acts, obviously, it will preserve also the support of mu, but in fact it acts transitively on the support of mu. And in the language I used previous lecture, it's exactly the same thing as saying that my measure mu, the uniform measure, on a periodic L orbit for some group, for some closed subgroup L of G. Now the problem with this naive conjecture, main problem is that it's not it's not correct for two reasons, and I'll explain the two reasons. One of them is a big reason, one of them is a small reason. So it's not true for, as far as I know, for two reasons. So one of them is a major region. It's somehow it could happen that maybe the support of mu, which lives inside G mod gamma, but is basically is contained in some G1 mod gamma 1 times G2 mod gamma 2 that is somehow embedded in G mod gamma. So it could just be that maybe G is a simple group, gamma is a lattice in the simple group, but inside it you could have such a product situation. The support of the measure is in this product situation, is inside this product, and somehow the projection of A to each factor, or to at least one factor, is not high rank. So this is a problem. If the early formulations of this type of conjecture missed this thing, and you could easily build counterexamples to them. So that's sort of something you need to be careful. You need to exclude this possibility. And there's another reason which is a bit less, you could somehow avoid if you phrase things a bit more carefully, but I don't really want to avoid it. I want to, because it's in some sense a material thing. So this is a major problem. There's a minor problem. And the minor problem, maybe it's best to explain by an example. So maybe X is something like SL2C times SL2C modulo SL2, the integer ring of Q joint I and square root of 3, or maybe this is a finite index subring of it. So this thing I could somehow, this the field Q adjoint I square root of 3 has two complex embeddings, or two pairs of complex embeddings up to conjugation, depending on whether you take square root of 3 to square root of 3 or to minus square root of 3. And you take every matrix here and you embed it in both ways here, you'd get a lattice. So this is a nice space. Inside it, it has homogeneous subspace, which is basically SL2R times SL2R modulo SL2Z square root 3 naturally sits inside X. Okay, so you have a homogeneous space, you have a homogeneous subspace. So far, everything is nice and beautiful. And then maybe your group A is basically the group generated by something like, I don't know, 7 plus I inverse identity, and the opposites, identity 7 plus I inverse. Well, if you start, basically you could take a measure like the natural measure on Y, which is homogeneous, and average it over, so basically a measure something like the natural measure so if you take the natural measure on Y and you average it, alpha, beta, you push it forward by multiplying the e to the I alpha, which is minus I alpha. Right, remember that I have here, the group is SL2C times SL2C, e to the I beta, e to the minus I beta. This applies to the measure of uy. This 1 over 2 pi squared. The integral here is from 0 to 2 pi. This measure here is going to be an ergodic measure for this action of A, and it's not homogeneous because of this ugly extra averaging, which is not somehow inside the group A. This is not a homogeneous measure, but it's going to be ergodic for this action. So it's sort of, you could say it's because I was not careful about how I define the group A. So you have sort of two solutions to the minor problem. You could either be more careful about definition of A, be more careful about what A is. So somehow the problem here is that I allowed complex eigenvalues. If I took just, if I insisted that my group A contains only elements which are diagonalizable over R with positive real eigenvalues, then this kind of problem will not occur. So that's one thing, or you could sort of be more generous what homogeneous or good mean, what a homogeneous measure is. And okay, usually Manfred and I went this way, but in my talk I want to go that way, because it's somehow, when you start talking about the Adels, which I would do later, and certainly when you start talking about the positive characteristic case, if you look about groups over function fields with positive characteristic, the second approach is actually the more natural. So I'll take the second approach. So here's the definition. I have two measures on some space X. So I have here an A prime are two, let's say, a billion. You don't have them to be a billion for the definition, but groups. And so and then A invariant measure on mu on, let's say, G mod gamma or whatever space you're working as, is equivalent by compact to an A prime invariant measure mu prime if there is some abelian group A double prime, so that A and A prime are co-compact in A double prime, such that if you do the average over A double prime over A of the shift of mu by A, it's going to be the average of A double prime over A prime of the shift of mu prime by A. Okay, so that's sort of exactly meant to handle annoying things like this. This is somehow, I'm going to ignore these type of compact nuisances. So I might take A prime to be, so what is to be something like square root of the thing generated by this and the other group, and then both of them are co-compact in the complex diagonal groups. So that would be a good example. And now you could basically conjecture so it's sort of a better conjecture. Here's now a conjecture. So if I have measure mu is either as in this case where you sort of its support is in a product group and it degenerates to the rank 1 situation in a very concrete way, or mu is equivalent by compact to an homogeneous measure. And that's a reasonable conjecture to make. And now, well, maybe I'll state our theorem. So I've worked on this problem for many years with Einstein, and we also have a paper with a talk on this problem, and I want to present one result. Somehow we had results, but not for a general diagonal group, but we assumed that the diagonal group was somehow of a particular kind. Maybe I'll state this, but this is sort of the theorem I would like to present. It's somehow we hope to sort of generalize it, but it's I think already interesting like this. Suppose you have a group G that is a form. It's a group over Q. It's a linear algebraic group over Q. And suppose it's a form of either SL2 to some power or PGL2 to some power. What does this mean? This would over the complex numbers. So this group is defined by equations over the rational numbers. The rational numbers are important, so they're part of the structure. But if you ignore this part of the structure, you think of it as a group over the complex number, then it becomes isomorphic to SL2 to the k or PGL2 to the k. I'll give some examples in a minute. So now I have G to be, that's okay, those sort of also S arithmetic extensions, etc. I hope somehow I have now to quickly, while I tell you, calculate what I'm going to leave out of the talk and what I'm going to include, not to take too much of your time. But anyway, I have my group, I have my lattice as usual, and I assume that gamma is irreducible. I mean, if not, then actually Manfred and I have a different theorem which handles what's called the joining situation. So it's not that it just, but I want to state something in a finite amount of time. Actually, in the poster, there's an application of the theorem that we have in the reducible case. So it's certainly interesting, but not today. So A in G is a higher rank, diagonalizable, etc. Mu ein wartender ergodic. So in this situation, the group is too small to have some example like in problem 1, so you don't have to worry about problem 1. I would require, like I had in the times 2 times 3 business, I'm going to assume some entropy assumption. For some A in A, and then you have two options. Which are sort of interesting. So either mu is equivalent by compact to a homogeneous measure on a periodic orbit a semi-simple subgroup L of G, and you could say more about that. You could sort of, or mu has homogeneous support. So the support is a periodic orbit and is supported on a periodic orbit of a solvable group. And again, I'm not telling you the whole story to save some time. This can only happen if G mod gamma is not compact. And in case 2, somehow you could encode what's sort of interesting, and something which we've sort of first encountered here is that in this case 2, you could sort of encode Rudolph's theorem into this, so sort of this way you could build, if you start with some, let's say, counterexample to Rudolph's theorem or counterexample to Furstenberg's conjecture, you could create measures invariant on such a quotient that somehow would be fall under this heading. So you have to be, if you could prove it, if you could just state that mu here is homogeneous, then in particular this would imply Furstenberg's theorem. And so we had results like that, even more general, but for instance in this setting we had to assume that the acting group is generated by elements which live only in one of the SL2 factors, doesn't somehow, and this gave us extra flexibility. And here we don't need to make this assumption. So now I'll give you, now you could ask, why is the case of unipotent groups harder than the case of diagonal groups? I mean, okay, why, can you explain why one of them you have to make some kind of entropy assumption, the other you can even try to prove quantitative results? And there's a reason for that, which is maybe also explains why entropy comes into the picture, which seems to be a bit strange to begin with. So for a unipotent group, if you use unipotent, then if you look at the measure, let's say, of those elements u in u, so there's the norm of u as a matrix, right? The norm of u as a matrix is less than t. This would be something like t to some power. Whereas if A is some higher rank diagonalizable group, maybe discrete or maybe not so important, but you look at the measure of those elements A and A for which the norm is less than t, that this would be something like polylog, which is of course much smaller. So the group is much smaller, and somehow you compensate for that if you take positive entropy. I meant to say log t to the power m, where m is some integer. It happens to be the rank of A, but I didn't. I meant to write a constant, not A. Yeah, it was sort of overusing a letter. Okay. So now what you could also look at, and I meant to explain it, but I mean somehow for some of you this would make sense. For some of you it won't make sense. I'll just say one word. If you could look at, if you have a group defined over Q, you can not just look at the real points of the group, you could look at the adelic points of the group, but you could sort of look at something, so maybe it's not so important what the adelic group adelic points are, but it's some ring in which Okay, it's not it's basically some kind of R times the restricted product over all primes of QP. But anyway, it's some ring in which Q sits discretely as a lattice, and then this quotient would be a nice space. And for somehow adelic tose, if you look at diagonal matrices, but now you allow the elements of the diagonal to be adels or idels or whatever, then suddenly the measure of those A inside this whatever adelic tose with the right notion of size, which less than t, would be something like, essentially the norm would again go like t to some power. And indeed, what I meant to present and don't have time is that in this case you can state a theorem without talking about without entropy. And now I have 2 minutes, so I want to. So this is sort of a fancy adelic theorem, but now I want to give a down-to-earth application of the fancy adelic theorem. It's sort of a cute application. I don't think this is something that is so easy to see elementarily. If somebody can see this elementarily, I would be happy to look at it. So now an application of this adelic theorem that I haven't stated. So suppose you have some number alpha and you look at the continued fraction expansion of alpha. So maybe I actually wrote down in my notes somewhere a continued fraction expansion of cubic root of 5. So this looks maybe something like 1, and then 1, 2, 2, 4, 3, 3. I know nothing about continued fraction expansion of a particular number, but one can look at. So if you have a number, the continued fraction of twice the number is some completely new continued fraction with no obvious relation. So this would be 3, 2, 2, 1, 1, 1. And this is going to be 5, 7, 1. And of course I can take more integer multiples of my number. And now, so these are the digits, right? So these are the digits. I can call this A1, or maybe this is alpha. This is A1 of alpha, this is A2 of alpha, etc. It's actually, I prefer to parameterize them not by integers, but by an arbitrary. So this would be an if when I take if I take so I have the sequence. So if pi over qi are the continuous fraction approximates to alpha, right? So these are pi and qi satisfy this usual recursion formula that pn is equal to an pn minus 1 plus pn minus 2, etc. So if qn minus 1 is less than qn, then I'm going to take the digit n. That's sort of, in some way, another way of parameterizing the digits of continued fraction expansion. And then here's a nice, well, I don't know, a theorem that I think is cute. Theorem that and okay, theorem is nice, and it's sort of also nice to have it as an application of this Adelic measure classification theorem. So this is Einsiedler and myself. It's actually also, it sort of strengthens an earlier result of Einsiedler, Fishman, and Shapira. So for every A, there exists some n, such that for every alpha, I should say somewhere for every q, at least one of A k alpha q, k from 1 to n is bigger than A. So in particular, and this was an earlier result of Einsiedler, Fishman, and Shapira, the supremum over n, the lim sup of the nth digit, or the supremum over k, lim sup of the an, of the nth digit in the continuous fraction expansion of k alpha is infinite, which was a conjecture of Bosher-Nitzan. But this is sort of a more, it sort of said that if you don't order these things like I did here, but sort of space the digits is the right way according to how fast the continued the denominators in the continued expansion grow, then on each one of the columns, at least one of the digits in this from this capital N possibility, that at least one of the digits is going to be bigger than A. Okay, so just to summarize 2 words, and then I'll finish. Basically, what the key point I try to make in my talk, if you're looking at diagonalizable group actions, there's a big dichotomy between the rank 1 and the higher rank situation. Rank 1, there's no rigidity. Higher rank, okay, you need to be careful, there's various caveats, but you get rigidity. In this higher rank, you expect few invariant measures, and with some entropy assumption, we know how to prove some reasonable results. These partial results, I mean, these are partial results of the conjecture, but somehow the nice thing is that they're already enough to prove some unconditional results that are of interest. And if you sort of are willing to look at the Adels, then sort of you're sort of somewhat happy, because if you could phrase various results in terms of Adelic groups that avoid this entropy assumption. At least they look cleaner. Anyway, thank you.
So is there the Adelic picture has a version of in characteristic P. Is there any interesting dynamics for Adelic groups in characteristic P?
Definitely. I mean, the situation in characteristic P is very interesting. Adelic, not Adelic. I mean, it's certainly. So one of the things that in characteristic P, the analog of Ratner's results are not known yet in the generality you would like them. But it is definitely, you could prove results, and sort of we've had some, there's some results of Einsiedler, Amir Mohammadi, and myself, this issue of this type in characteristic P. But sort of one thing you have to be careful in characteristic P So I told you that in characteristic zero, let's say, you sort of can avoid this issue of having measures that are not homogeneous if you're careful and take your elements diagonalizable over a small field, maybe R, or in the positive characteristic, somehow any field has a subfield, so this problem is somehow harder to avoid. But it's sort of, yeah, definitely it's very interesting, and it's you could say some things, and there are some things you don't know, so it's sort of definitely an interesting area to look at.
Yeah, in almost every talk, a question what happens in characteristic P is a good question.
Yeah. I'm not sure if it's true, but in this talk it definitely is.
So another thing, so there is the Langland's program which studies harmonic analysis on this quotient. Is it helpful in any way in this type of questions?
So, I mean, the relation to automorphic forms is certainly a deep one. One of the first applications of this kind of theorem was to study, it's not really in the Langland's program, because the Langland's program you sort of don't care to look at functions, but if you look at the Hecke mass form in some quotient of a group, you want to maybe, you take a sequence of these, you want to maybe show that the absolute value squared converges to some uniform measure. This is sort of related. I mean, there's definitely very interesting relations between the automorphic. I mean, at the end of the day, automorphic forms people study GA modulo GQ from their perspective. We study either GR over GZ or GA over GQ from our perspective, and obviously there's sort of interesting interaction between these two. And also in characteristic P, Langland's program will have applications to questions that we studied. One of my, in some sense, dreams is to use the fact that in characteristic P you know so much more about these kind of things to prove interesting things dynamically, and maybe even if you really, if you want to dream, you could sort of allow yourself to dream. So maybe you could somehow use the Langlands and dynamics to prove something in characteristic P, and then somehow magically move it to the characteristic zero, and then be really proud of yourself. Yeah, so that's certainly, for instance, yeah, and sort of that was not an uninteresting result. So.
Any other questions?
Pablo just psychically takes all our questions.
Yes, I was going to ask it one time. All right, looks like there are no other questions, so let's thank Professor Lindenstrauss again.
Thank you.